Okay, this is Andrew. I'm back. I'm going to do a presentation on variable length subnet masking. This presentation is going to give you an idea of what variable length subnet masking is, why we need to use it, and it should give you all the details you need to do if you choose or are required to do a variable length subnet masking problem. Okay, let's get started. So let's take a look at this network, and we have 3 routers, okay, and 3 switches. And off of these routers, we have 25 PCs off router A, 60 PCs off router B, and 120 PCs off router C. And then we've got the routers connected in this manner: A to B, B to C, and then C to A. And these are just cables plugged into the ports on the routers. Okay, so the question is then, if I tell you that each branch being this is a branch, and this is a branch, each cable plugged into a router forms its own network. How many networks do I have here? Well, I actually have 1, because that's 1, 2. Now, branches plugged into a switch don't form their own network. It's on the same network, considering it's a layer 2 switch. Okay, so 2, 3, and then between the routers, this becomes one network, and then this becomes one network, and this becomes one network. So you can see between these routers, I only need 2 IP addresses, right? But here I need 25 IP addresses. Here I need 60 IP addresses, 1 for each computer, and here I need 120 addresses. But so that's the thing is I have 6 networks. 3 of them need 2 addresses, 2 IP addresses each. 1 network needs 25, 1 needs 60, and 1 needs 120. So it's actually 6 networks with a total requirement of 211 addresses. Okay, so we need to get a network, an IP addressing scheme that works, that best suits our applications for this new network we're building for a company. So the question is, what's the best way to do that with the options that are available to us? So I go to my service provider and I say, okay, we need to buy a network scheme. What's the options? And I say, okay, you can buy a class A, B, or C. This is kind of an overview to give you an idea. Okay, so they say the 8-bit is the size of the network is 8 bits, and the number of host bits is 24, which gives you a total of over 16 million host addresses, 1 for each PC. Do we need 16 million? No, clearly not. And the class B has 16 bits for the network, and then 16 bits for the host, which provides over 65,000 IP addresses for the host. Do we need 65,000? No, absolutely not. So then they say the class C gives us 24 bits for the network and 8 bits for the hosts. And that provides actually 254 IP addresses for the host. So with 207, we have a number of options. We could potentially buy 6 different networks, 1 for each. One class. We could buy 6 different C class networks, 1 for each of the networks we need. But what's the problem there is we have 254 available addresses, and we only need 2 here. For each of these 3 networks, we only need 2, so that would leave 252 and 3 networks that aren't even being used. Well, first of all, network addressing costs money, and then second, it's wasting them as well, because there's only over 4 billion network addresses available in the IPv4 scheme, and those are pretty much all used. That's why they're switching over to IPv6. So you certainly don't want to, for 2 reasons. You don't want to buy addresses you don't need because it costs money, and 2, you don't want to waste them. So I give all these options, call my boss, and she says, okay, get 1 class C and we'll subnet it. And that's where the variable length subnet comes in. So we're going to take a look at this. So we're going to do a quick review of numbers here. And I know Everybody knows this, so let's take a look at the number 2,543. So 1 times 3 is, so this is your placeholder. So you have a 1 here, and this is your decimal, your tens. This is by tens. So you have a 1 in your first place. This is your ones place. Multiply that by 10, 1 times 10, and this is your tens place. Multiply that by 10, and then this is your hundreds place. Multiply 100 by tens, and this is your thousands place. So each time you go to the left here, all you do is multiply by 10. So you have 2 times 1,000 plus 5 times 100 plus 4 times 10 is 40 plus 3 times 1 is 3. And you add them all up, it's 2,543. And we all know that, but the reason we did that is to just do a quick review of the binary, only in the terms that you're going to need for the variable length subnet masking. So let's take a quick look. Instead of going by 10 now, you just go by 2. So it starts at 1, just like here, and the next placeholder is multiplied 1 by 2. So this is your 2's place. So the next one is 2 by 2, 2 times 2. So this is your 4 place. So then the next one is 4 times 2. So this is your 8 plate. So you have a 1 here. That's 8 plus 0 plus 2 equals 10. So this binary number is a 10. So we should all be able to easily do that. So the problem is, when we're dealing with IP addresses, what we just did was called a 4-bit. But an IP address in an IPv4 is done by bytes, which is 8 bits. So take a look at this example here. What's this binary number? Well, let's take a look at the 8 bits first. Each one of these is a bit. So this is 1 times 2 is 4. 2 times 2 is 4 times 2 is 8. 8 times 2 is 16, 32, 64, 128. You get the idea. So if I have a 1, 0, 0, 0, 0, 0, 0, 0, what's that? What's that number? What is that in decimal? Right, it's 128. 1 times 128 plus 0 plus 0 plus 0 plus 0 is equal to 128. Great. So let's try one more. So if we have a 1 here and a 1 here and the rest 0, so what is this binary number in decimal? 1, 1, 0, 0, 0, 0, 0, 0. Okay, it's just 128 plus 64 is 192 plus 0 plus 0 plus 0. So it's just 192, right? Okay, so let's go ahead and complete that table in that manner. So this 1110000 is just 128 plus 64 plus 32 is 224. 128 plus 64 plus 32 plus 16 is 240. So you get the idea. The next one's 248. The next one's 252. So believe it or not, with just these numbers, this is pretty much most of what you need to do variable length subnet masking. As complicated as it can be, this actually reduces the problem quite a bit. So let's take a quick look here. Okay, so here's an actual network address, and then here's its subnet mask. Okay, so the 255.255.255.0, this number tells you which bits of your network address are going to be network bits and which ones are going to be host bits. Okay, so this is the same thing. This 255, if you go back and do the 128 plus 64 plus 32 and add all these up, you're going to get 255, because the biggest this number could be is 255, and that's all ones. But understand that this is actually 2 to the 8, which is 256 because 0 is included. So you have 256 numbers in each one of these quadrants, but the actual number can only go 0 to 255. So you can see here, all ones is a 255. Okay, all ones, and 0 in decimal is just 80 host bits. So this is the network bits. So this is what I bought, was the class C, right? He said there's 24 network bits and 8 host bits. So this is it. All right, so how many did we just say? There's 24. So that's a /24. So this is what's called CIDR notation. And CIDR notation, this is the same. This is just a different way to represent the subnet mask. is the /24, because basically the 255s are ones, so this is telling me there's 24 ones. And then since the whole thing is 32 bits long and there's 24, then we know there's 8 left for us to do with what we want. So really what we bought with this network address right here was the ability to take these 8 bits and do what we want with them. And what does that mean? That means we can assign some of these bits in here to networks and some to hosts. So that may sound complicated, and it can be, but it's also can be not too bad. So let's take a look at it. All right, so let's do one more. If I took this bit right here and changed it to a 1, what's that in CIDR notation? A /25, obviously, because what happened is we added one more network bit. So this is a /25, or that was a /24. Okay, great. Well, now we know what a /25 is, but so let's go ahead and do one more. All right, so we know what the /25 is. It's one here. Let's try one more. So what happens? Well, first of all, if you looked at this byte and it's 10000000, we know what the CIDR notation is /25, but how do we get the subnet mask from the /25? Look at this byte, it's 1000. What's that binary number in decimal? Well, we already did it, right? 10000000 is a 128, so you put it here. So the subnet mask, this CIDR notation is equal to this subnet mask. And the thing is when people write this, they'll usually write it like that. But not all, but certainly Cisco's equipment and most equipment, you have to enter the actual subnet mask. You can't enter CIDR notation. Although on some equipment you can enter CIDR notation. So that drives the motivation from going back and forth between CIDR notation and subnet masks, is because humans generally don't want to look at this. They can just understand this as 25 network bits very easily. But the machine has to see this, has to see the subnet mask. So you have to be able to convert back and forth, because if you're given to it on a piece of paper or something, usually they write /25, but when you enter it in the machine, you have to do 255.255.255.128 if it's a /25. All right, great. So let's do another one. So if I make another one of these bits a 1, then that becomes a /26, obviously, because we have 26 network bits. Okay. Well, what is 26, a /26 in CIDR notation? How do I represent that as a subnet mask? Well, same thing. Look at this byte here. When I had 1100000, that was 128 plus 64, which was a 192. So put your 192 here. So the actual beauty of subnet masking is you can't have like a 1101. That doesn't make sense. The network bits have to be continuous. So this is all you can have. So you would have a /26. You would have a /25, a /26, 27, 28, 29, or 30. And really that's all you're going to have is a /30, because remember before when I said 256 is the highest number you can have here? Well, if I have 252 for the networks, then what's left? 256 minus 252 is 4. So that means 4 is all that's left. But I have to save my lowest one for a network address, and I have to save my highest one for the broadcast address. So this /30 actually only gives me 2 IP addresses, which is what we were looking at, and that's just a link between 2 routers is where you're usually going to use that. So there's not anything smaller. So that's what I'm saying is the beauty of this is all you have to remember, basically. And you don't even really have to remember it, because it's easy to just derive it. It's 128 plus 64 is 92. plus 220 plus 32 is 224 plus 16, and you notice each one of these is half. Instead of, if you go backwards, instead of going up by 2, you just come down by 2. So eventually, with a little practice, you can easily do all these problems in your head if you just remember those simple concepts. So we already discussed this as 1 byte is 2 to the 8, which is 256. If I have 192 here, what's left? 64. So that's the block size. So that means my block size is 64 because the total size of this is 256, 0 through 255. Okay, so 192 actually makes fewer host addresses, but the block size is just 64. And actually, if you went ahead and looked at 1, 2, 3, 4, 5, 6, if you look 2 to the 6, that equals 64. So you can do it either way. 256 minus 192 or 2 to the 6. So you can do 2 to the host bits. Or the only reason I don't like that is these aren't really, they call them host bits, but they aren't really host bits because you have to save they are host bits, I guess, but you have to save the network address and the broadcast address out of that, so you can't really use them all for hosts. Okay, so let's go ahead and take a quick example here. So if I have a /25, which we know puts 1 bit in our byte in the 4th quadrant, which gives us a subnet mask of a 128. What's the block size? The block size is just 256 minus 128, which is 128. So let's do another one. If I take the byte in the 4th quadrant and I add 2 network bits on the left, that gives me a /26. So we already did that. And 128 plus 64 was 192. So we already did it. So that's our subnet mask, 192. So what's the block size? Well, the total space is 256, and we've used 192 for network, so there's 64 left for host bits. Okay. But this is really the block size. So let's go ahead and finish this table. So again, if I do the first 3, then that gives me a 224, which was just 192 plus 32, 224. So here, what's left? 32. So 256 minus 224 is 32. So similarly, so you can easily see these. The 240 is 16, 8, 4. All right. So you got the block size. Now we need to know the host, which is really how many IP addresses we get out of these. So it's simple. You do the first is the network address and the last is the broadcast address. Don't worry about it right now. We're going to do an example. So just know that the block size minus 2, what this means is this is the number of IP addresses you have available in this /25 is 126. In this /26 you have 62 IP addresses available. In this /27 you have 30. So okay, we had one with 120. Would this /26 give us 100? We had one network with 120 computers. Would this /26 give us enough IP addresses? No, absolutely not. So for the 120, you can clearly see that we would have to have a block size that's bigger than what we need. Okay, so let's go ahead and take a look at the actual example. So 3 subnets of 2 addresses. So we're subnetting this /24. Okay, and we have a subnet of 25 IP addresses for the 25 computers. So let's go ahead. You always start with the biggest one first. So we have 120 IP addresses. Well, we already did that. We know we need, this is not enough. So we know we need this. We need a /25. So let's choose the /25. All right. So the network is 192, the lowest one, 192.168.1.0. The highest one is going to be 128 more, but since we're starting at 0, that gives us 127. So the IP addresses that we can use are in here. 192. Now remember, we're only changing this side. So these are the IP addresses that we can use. Okay, and that's a /25, which is a subnet mask of 128. Okay, so we did the first one. We did the 120. So now let's do the 60. Okay, so the 60 is, we need 60 IP addresses. Is this /27 big enough? No. Is this /26 big enough? Most certainly. So we're going to use a /26. Okay, and what is a /26? We've put 2 bits in the fourth quadrant. We've added the 2 bits on the left to the networks. So that's 192, right? It's 128 plus 64 is 192. Now what's the block size? The block size is just 256 minus the 192, which is 64. And then the block size minus 2 is the number of IP addresses, which is 62, and we need 60, so that'll fit in there. Now, this is going to, in real life, you know, your boss may say, well, let's leave 20% extra for growth or whatever. In general, you don't want to fit 60 into 62 because you may need to add more, especially these days with bring your own devices. People are always, adding on their tablets and whatever. So you do want extra ones. This is an example to give you the idea. Okay, but be aware that you do want to have extra IP addresses. Okay, great. So we know we want to do the /26. We did it. Now what's the lowest one? Well, on the /25, remember we only have 256 a space of 256 available, and we used 0 through 127. So now we have to start at 128. Okay. And if we add the 64 onto that, then we stop at the 191. So this is your broadcast address. This is your network address. And then the 129 through the 190 is your usable addresses that you'll assign to the PCs in the subnetwork that uses 60 addresses. Okay, great. Hopefully you get that. So let's do one more. So a subnet of 25 addresses is going to require what? Will this one work for it? No. Will this one work for it? No. Will this one work? Yes, absolutely. 30 is big enough, so we can use a /27. Now you could use, like I said, if your boss said, okay, well, we want at least twice as many, so you would want to use a 62. But it'll fit in this space. But you could use a bigger space if you like, but you can't use a smaller space. All right, great. So the last one we ended at 191, and our total space, because what we've done is we're taking the space of 256 that goes from 0 to 255 in the fourth quadrant. We're taking it and we're dividing it up into smaller chunks to fit these block sizes in it. So the /27 is going to give us, if you look at 128 plus 64 plus 32, that's the first 3 bits, is going to give us a 224. The 256 minus the 224 gives us a block size of 32, minus 2 gives us 30 hosts. Okay, so that's a 224. And we have to realize our block size is 32. We ended at 192. So if we start at 192 and add 32, we end at 223. So at 223, that's the broadcast address. This is the network address. These are the usable IP addresses, 193 through 222. So let's take a quick look at, these are the 2s, right? So see if I can go back. Previous. So this, we discussed this, is we have to use this for 2 because we have the broadcast and the network. So we want to use a /30. This is our link between the routers that only needs 2 IP addresses, 1 on each side. So you want to use a /30, which is a subnet mask of a 252, and we did 3 of them, right? So now we realize that that's 4, and the last one we ended at 223 in our space in the fourth quadrant. So now we're going to add 4. which gets us to 227, and then 225 and 226 are the usable IP addresses. And then similarly, but for the links between the other two routers, we're going to use these two. So now let's just tabulate all up in a table and put it on our diagram. So you can see here, this was our /25 network. This was for the 120 clients. So over here we used our low IP address, which is 11, going up to our high IP address, but we only need 120, so we stop at 120. We don't, so we have some extra here, like 5 or 6 extra, whatever. So now let's take a look at, always start at your largest and work your way down. All right, so on 60, we have a /26, we did that. We start at 129 as our first IP address and 190 as our last. So we're going to count up 60 from here. So 192. So this would be your DHCP pool, correct? This would be your DHCP pool. All you would have to do is enter this DHCP pool on a router or a DHCP server somewhere, and it would issue, they would go through the whole process of assigning a dynamic IP address to the router, to the hosts. All right, so you get the idea. I'm not going to go through every one of these. We'll do one of the twos. So look at the /30. That gives us two IP addresses, 225 and 226. We did it right here, 225, 226, and here's the network. The network is 192.168.1.224. So there's the network, /30, and then the .225 is here, the .226 is here. This is often the way you're going to see it written. And then when you have to enter it into the machine, like when you have to program this IP address onto this router, you're going to have to put it in as a subnet mask. That's why you need to be able to go between both the subnet mask and the CIDR notation, okay? So you'll often on diagrams, you'll be given the CIDR notation, and then you have to enter it in the machine in the subnet mask. Okay, so also, I might want to do just one more video that shows you, in real life, you don't do this physically. You have to do this for like certification exams. This is the type of stuff you really need to know because, you know, let's face it, anybody can memorize configuration commands or whatever, but if you can do this, these type of things are interweaved through many of the problems, and if you can do them quickly, then you have a leg up on passing the exams. Okay, so also you may have to do this stuff in interviews, but in real life you would just use a variable length subnet mask calculator, and maybe we'll take a quick look at that in another video. All right, well, thank you very much. I hope that helped you out, and I hope it gave you an idea of why you need variable length subnet masking and an idea of the details of how to do it. All right, thank you.